My name is John Kunze, and this presentation was co-developed with Donnie Winston. I'm a computer scientist who, for over 20 years, worked with the University of California with data centers, libraries, museums, and archives. In Berkeley, California, which is my virtual background, I wrote software tools that come pre-installed on all of your Mac and Linux systems. Then I moved into information systems and preservation standards, where I became the main editor or author of the first three metadata standards, which was Dublin Core. And before that, I wrote the formal requirements that moved the first URL standard over the finish line. Both of those standards are important for identifiers, this topic. The trick to getting the URL or web link standard approved was actually to allow or make it okay for URLs to be breakable, leaving persistent URLs for a future standard. So in a way, broken URLs are my fault, and it's my punishment is that many years later, I'm still working to fix them. Now, if you're wondering what a persistent identifier is, it serves the same purpose as a permalink. It's meant to persist, but there are no guarantees. So we're talking about URI or URL identifiers that were aspirationally persistent when created. So why should we care about ARKs? The average lifetime of a URL was once said to be 100 days. At the end of its life, a URL link breaks, usually giving you the dreaded 404 not found error that most of us have seen. While that can be irritating, it's a minor disaster for memory organizations. So ARKs can serve as robust links for any kind of thing in any discipline. The ARK scheme is one of 5 so-called persistent identifier or PID schemes. There's been a great deal of nonsense written about PIDs. Some of it is described in a Twitter thread called 10 Persistent Myths About Persistent Identifiers, which is available at the link using this example ARK or the QR code next to it. PIDs are permalinks containing hints that make them look different from the average URL link. So every URL is potentially persistent, but some people think it becomes persistent when it acquires some superficial syntax differences, such as the ARK colon in this example, or when you see the domain name doi.org at the start of the URL. This nonsense was in full bloom in the late 1990s, but it eluded the debate about the 4 proposed PID schemes. That's why the Archival Resource Key or ARK identifier scheme was introduced in 2001. Wait a minute. General artificial intelligence, Gen AI, is here. Are we stuck in the past talking about old-fashioned things like identifiers, preservation, and metadata? No. How do you verify a dubious claim from AI? Check the sources. If a claim doesn't cite sources, it's automatically subject to some level of doubt. But how often have you seen these sources cited? How much do you know about the software tools that created each step of the AI pipeline? What about all the models and the data and content they're based on? We hope someone is saving these artifacts due to the financial and environmental cost to regenerate them. Of course, we need to cite them too. How do we discover these sources? The scientific and cultural heritage world has been kind of dazzled by Gen AI and seems to have lost some interest in the old-fashioned metadata preservation and permalinks, but we need them now more than ever. Here's what an ARK looks like. At first sight, it's a URL that carries this internal label. To the right, the 5-digit Name Assigning Authority number, or NAN, identifies the organization that created the ARK. Further right, after that number, is the local name of the thing that the ARK is assigned to. To the left, the host name makes the ARK actionable or something you can click on. It's also known as the resolver. ARKs are unusual among PIDs in allowing organizations to run their own resolvers. The part starting with the ARK colon is the core globally unique identity. It does not depend on the host being available or on the future existence of the World Wide Web. In the previous example, you saw n2t.net, which is a global name-to-thing resolver. This is the main ARK resolver. So why doesn't it contain the letters ARK? Well, one goal of ARKs was to break out of the silos and walled gardens surrounding many identifier systems. So what got built was the name to thing resolver, or N2T. The domain name n2t.net is short, which is helpful in citation strings. Another big benefit of N2T is that it resolves over 900 compact identifier types. So if you forget where the resolver is for ISBN, Protein Data Bank, or KEBI IDs, or for ORCID, ROR, Handle, DOI, or ARKs, just remember n2t.net. Not only does it track them for you, but it reduces the reliance on individual host names. And its compact identifier support saves precious visual real estate in citations. ARK organizations include a wide variety of memory institutions, nonprofits, for-profits, data centers, and government agencies. A few are listed on this slide. At the lower right is another example ARK identifier, which you can recognize by the signature ARK colon inside it. This one points into the collection of the Louvre Museum. What are ARKs used for? Here are some examples. The biggest ARK user is the Family Search Genealogical Research Organization. Next is the archive of source files for journal content published in the global north. The Internet Archive has been assigning ARKs to scan books and texts since 2008. The French National Library was an early adopter and has a wonderful image depicting the biblical ARK. ARKs are also important for people, especially historical figures. For example, 19th century mathematicians Ada Lovelace and James Maxwell do not have ORCIDs, but they do have ARKs. So these ARKs are kind of like ORCIDs for dead people. Finally, there are several projects assigning ARKs to vocabulary terms. This example shows the NAN, the name assigning authority number reserved for Emory University. Inside the red rectangle is the ARK they assigned along with its 5-digit NAN. This shows an ARK in compact form because it has no resolver in front of it. Here's another compact ARK showing the NAN for the British Library. Again, those 5 digits are the name assigning authority number. Morphosource is a data repository where you can interact with 3D and 2D media from the world's natural history, cultural heritage, and scientific collections. And here's an example using their NAN, which is 87602. And here's another example from the University of Toronto Scarborough Library, which, by the way, has released their in-house library system for ARKs open source. Their NAN is 61220, and they are stewarding student creative writing assignments with ARKs. Again, you can see one of them here inside a URL, underlined in blue along with their 5-digit NAN after the ARK colon. This example shows the NAN reserved for the Leventhal Map and Education Center. Inside the red rectangle is the ARK they assigned along with its NAN. Again, compact form of the ARK because it has no resolver in front of it. Note the slash following the colon after the ARK. That's an ARK in classic form. Finally, here's a look at an ARK at the Internet Archive whose reserved NAN is 13960. On the left is a major library standard that was digitized and deposited in their text archive. And on the right is its metadata record. Inside the red rectangle, you see the ARK they assigned. Again, this shows a compact form ARK, no resolver in front of it. There are other fields. There's an identifier field above it. The ARK is more opaque than what's inside their in-house identifier. People find opaque identifiers to be, well, opaque, but fortunately you can see a bunch of metadata above that. That metadata includes 2 URN identifiers, also persistent identifiers. Having multiple identifiers may not be ideal, but it's common, and it's good practice to keep all the identifiers that come in with an object. Looking back at those examples, some ARKs had an extra slash in them. The extra slash doesn't change the meaning, and it appears in what we call classic ARKs. The modern practice, however, is more streamlined without that slash after the colon. The modern form is preferred, but both forms are considered equivalent in perpetuity. After all, broken links aren't a good look for persistent identifiers. So every URL is potentially persistent, whether or not it looks like a PID. Nor does a URL become persistent when you put a label like permalink next to it, or when the identifier starts to look like a PID, such as the ARK colon or DOI.org added to the front of it. Identifier syntax is not magic. It's never more than a suggestion that this link may be more stable than the vast majority of URLs that are produced with no thought for preservation. Every PID is aspirational, based on the hopes of its creator, and there are no guarantees. As a result, PIDs break often by the hundreds of thousands, and that's normal. Committed preservation providers will repair those links that can be repaired. Keeping PIDs persistent often involves the fundamental technique of indirection, which we'll get to next. Maybe this is a reminder for some of you. It's a core PID technique of indirect identifiers, which uses the HTTP redirect concept. So here's normal direct access. A user clicks on a URL in a web browser, which sends it to the web server appearing at the beginning of that URL, and a page is returned. With indirect access, the first server contacted says it doesn't know where the thing is, but it returns a message saying this other named server should have more information. Behind the scenes, instantaneously and unknown to the user, the browser restarts the process by contacting the second server. There could be a third server, fourth, fifth, etc. This is web redirection, and it's like forwarding snail mail to a new address. Many of our ordinary web accesses involve long chains of multiple redirects, all taking place quickly and without the user being aware. All PIDs are very similar in structure. They all follow one pattern and have one basic trick, namely the simple web redirection that's been built into every web client and server for 30 years. Near the bottom, you see what ARKs look like, and above it, all the other PID schemes have very similar form. They start with a resolver, then a name assigning authority, and finally a local name. For example, Orchid and Roar, they're newer PID schemes using the same pattern and trick. So ARKs are similar to DOIs. Both are PIDs for content and metadata, and ARKs are found in many of the places where you find DOIs. In contrast, ARKs come with no fees, no limits on how many you can create, and no metadata requirements. Recently, ARK adoption has been especially strong in the global south and from under-resourced institutions. From the beginning, ARKs have been decentralized and can identify any kind of thing, digital, physical, or abstract. Finally, there's no conflict using both ARKs and DOIs together, which is common in museums and libraries. Some people assign ARKs to everything, and for a subset of things that later need DOIs, they can derive them from the existing ARK strings. This next example is from the Smithsonian, whose NAN is 65665. You can see that number at the beginning of each ARK. You can also see the wide range of their object types: biological specimens, paintings, photos, and sculpture. Note the long opaque names they've assigned, which were generated using the UUID software that's pre-installed on nearly every platform. These unique names are long, unfortunately, but they're also very easy to generate. Here's some more details of ARK syntax, including subparts and variants. But right now, let's just focus on the part in the middle, the NAN, or the name assigning authority number. So the NAN is a 5-digit number. As such, it is opaque, which is good for longevity. But what if you want to know what's behind that opacity? Well, in a browser's address bar, you can try truncating an ARK so that it stops after its NAN, as shown in the yellow highlighting. This is a stub ARK. If you hit enter after this incomplete ARK, it lets you inspect the 67375 NAN, which is from our first case study. I invite you to do that while listening if you can multitask. We can also try this with other NANs. Or you can try backing off further to a shorter stub ending with just ARK colon, and that tells you about the ARK scheme. I mentioned that N2T can serve hundreds of other schemes. For example, try entering the protein databank identifier shown on the last line. Here's what part of a record looks like when you ask N2T to tell you what the 46171 NAN is. You get the record for the National Autonomous University of Mexico, as well as when it was registered in 2017. Very importantly, it tells you where the N2T resolver should redirect incoming ARKs so that they get sent to the correct local resolver. All the NAN results that you can see by playing with stub ARKs in the address bar, they're all pulled from the main NAN registry. This is just a plain text file that you can look at directly in your browser. You can use the QR code if you're interested. Here are some fields from another example record for the National Library of France. So the ARK has, the NAN has two main purposes. It's a lookup key for the resolution reference point, and by defining the root of a global namespace, it isolates an organization's autonomy and responsibility for assigning its ARKs. That way, without interfering with anyone else's assignments, an organization can determine its own policies regarding identifier form, uniqueness, and even reuse. Basically, just as for URLs under its domain name, an organization can freely assign ARKs in any way that it wants. Here's a link to the form you can use to request a NAN for your organization. If you want to practice using it, just indicate in the final comments that you're filling it out as a training exercise. We have a team of volunteer curators who receive these requests, and we try to turn requests around within 48 hours or 2 business days. So this shows some more details of the ARK syntax. We talked about the NAN that comes after the ARK label. Moving further right, the special characters / and dot or period have reserved meanings in ARK suffixes. So that makes those characters effectively non-opaque. They help the recipient make inferences about one resource containing another or one resource being a variant of another. In an ordinary URL, you could guess at similar interpretations, but in ARK-based URLs, the guesswork is gone. If you use the reserved characters, you are formally declaring that these relationships exist. There's a natural parallelism between ARK suffixes and the popular IIIF image API, which is being used in domains with lots of images, medical research, museums, botanical gardens, etc. If you have IIIF images, you can create and manage one ARK for the image and just change the suffix to identify millions of subparts and variants. This works if the local resolver supports something called suffix pass-through, which I'll talk about in a minute. So here's an example from the French National Library. In this long IIIF compliant URL, you see an opaque base name after the ARK colon and the NAN. Then you can read the page number F29, the comma-separated coordinates of a rectangular region, the request for full quality, and the JPEG format. So there's an opaque base name and a less opaque suffixes. Tools for implementing ARKs can be found in the resources area of the ARK Alliance website. They include minters for generating unique opaque strings. They include resolvers, plugins, and an ARK service for library administrators. There's an important technique of suffix pass-through, which is supported by a very interesting tool that is a hybrid of the Internet Archive's ARKlet tool and with modifications from the Frick collection, the art museum in New York City. Suffix pass-through is this feature that a web server can choose to support in order to greatly increase the number of identifiers that it can forward. It dramatically reduces the burden of maintaining identifiers by permitting one identifier to stand in for millions. The way it works, given a URL for the stored identifier, if an ARK arrives with an appended suffix, it will be reappended or passed through to the destination during resolution. This is critical for IIIF applications so that the many addressable subparts and formats don't all have to be separately registered, maintained, and possibly paid for. ARKs are naturally compatible with linked data because they are expressible either as compact URIs or as full HTTP URIs. Even in the case of a non-resolving ARK, recipients can still learn its origin by reading the name assigning authority at the beginning. And as PIDs, they help protect our longer-term investment in semantic web and knowledge graph applications. So there's a linked data rule that says, URIs should lead to other URIs in order to help people discover more things. While that's routinely honored in the ARK metadata, it's always honored implicitly by the ARK syntax and its suffix conventions. As a reminder, those slashes represent hierarchy that a client can expect to traverse, and periods represent the resource variants, such as .jpeg, .pdf, etc. These are things that a client can expect to elide they want to receive default representations. And here's a little technical slide very briefly. You may be able to implement ARKs almost trivially by leveraging the way you already mint and manage your URIs. Often there's a core opaque identifier somewhere in your system. And so you may be able to skip minting and go and implement, for example, just map incoming ARKs that you've applied for and map them using one rewrite rule in your Apache or server configuration file. So this, you could say, well, it takes an hour, but in a production setting, it probably takes a week to check everything's right. But that could be a trivial ARK implementation. So here's a slide about ARK metadata. To request metadata, you just append a query string consisting of !info. This shows minimal metadata, who, what, when, and where. The !info is an ARK inflection, which is an easier and more generalizable way to do content negotiation. ARK metadata is extremely flexible, from none to anything. And that includes metadata normally associated with DOIs. For example, many ARKs return metadata in the DataCite profile. This is useful for ARKs identifying journal content. Persistence is not binary. It's not on or off. It is nuanced because, ironically, preservation often involves change. Valuable objects tend to be complex human-managed clusters of digital artifacts that curators are forced to change in order to keep up with changing requirements and user expectations. Requirements range from technical, policy, security, and legal requirements. All of these things, we're constantly tinkering with our objects. So they're not actually frozen. One example is larger thumbnail image sizes. Every 5 years, the storage capacity and network capacity improves, and 5 years ago, thumbnail sizes just don't cut it 5 years later. We also get improved OCR algorithms, and although the OCR output may change, not many people complain about that. Another example is maybe a long-term stable release of the Linux operating system. It's long-term stable from 3 years ago, but why is it still getting regular security patches? And the answer is because of security patches, and those are more important than most people's idea of absolute frozen preservation. So that's where we need new vocabulary terms to describe these nuances, plus the ability to keep refining and extending those terms to keep up with the changing digital landscape. So here's a paper from 2017 that proposed a dozen terms not finalized. They touch on ARKs in several ways. They directly support persistent statements, And each term is also identified by an ARK pointing into a metadata dictionary. I think I'm about to run out of time. Is that correct? Probably. So let me just zoom ahead. Um, I'm skipping the metadata dictionary vocabulary we built, and I'll show this final case study using a visualization from the U.S. National Science Foundation iSamples project. It allows us to visit the South Pacific island of Moorea in French Polynesia. Each of the colored points represents a physical sample, and the towers indicate that many samples were collected at the same location. Each sample point has an ARK identifier, which is displayed when mousing over it. Clicking on one of the points brings up summary metadata, which allows you to link back to the original collection. Following that link to the Smithsonian, you can find more details about the specimen with cross-references to analyses, publications, and other material. The interlinking is done with millions of ARKs, and the open source software can scale to accommodate hundreds of additional collections. Currently, the iSample system assigns identifiers to biological specimens, rocks, and archaeological artifacts. The ARK Alliance was formed in 2018 to sustain the ARK infrastructure, and we welcome input and volunteers for our working groups. We have mailing lists, mailing email forms in 3 languages, and I think I've got to stop here.
No, that was excellent. Thank you. Right on time. And thank you for your flexibility in the schedule change today. We do have about a minute. Does anybody have any questions for John? No, not at this moment. Okay, well, thank you. Thank you for your time. Thank you for coming and sharing that information with us.